Good day everybody. Today I would like to discuss about the using of clausius clapeyron equation. Meteorologists study the atmosphere in an attempt to understand and ultimately predict the weather. See figure 3.4. The Earth view satellite. Weather prediction is a complicated process, even with the vast data. Meteorologists study chemistry, physics, thermodynamics, and geography, in addition to specialized courses about the atmosphere. One equation used by meteorologists is the clausius-clapeyron equation, which is usually introduced in chemistry classes and examined in more detail in advanced thermodynamic classes. Rudolf Clausius and Emil Clapeyron were physicists responsible for the early development of thermodynamic principles during the middle 1800s. See figure 3.5a and figure 3.5b. In meteorology, Clausius-Clapeyron equation is invoked to determine the relationship between saturation water vapor pressure and the atmospheric temperature. The saturation water vapor pressure can be used to calculate relative humidity, an important component of weather prediction, when the actual partial pressure of water in the air is known. The Clausius-Clapeyron equation is ln VO divided 6.11 equal delta HV divide air time 1 divide 273 minus 1 divide T. Okay, that is the Clausius-Clapeyron equation. We will discuss more detail in the next page. This portrait of a Rudolf Clausius and the Emil Clapeyron, scientist, physicist, and the VO is the saturation vapor pressure for water in millibar at temperature Kelvin, and delta HV, latent heat of vaporization for water, equal to 0.453 times 10 degrees 6 joule per kilogram. Air gas constant for moist air 461 joule per kilogram. T, temperature in Kelvin. It is rare that temperatures on the surface of the Earth are lower than minus 60 degrees Fahrenheit or higher than 120 degrees Fahrenheit. Use the Clausius-Clapeyron equation to find the saturation vapor pressure for temperature in this range. Present your result as a table of Fahrenheit temperature and saturation vapor pressure. Study the problem. Find the saturation vapor pressure at temperature from minus 60 degrees Fahrenheit to 120 degrees Fahrenheit using the Clausius-Clapeyron equation. 2. Describe the input and output. Input delta HV equal to 0.453 times 10 degrees 6 joule per kilogram. Air for equal to 461 joule per kilogram, and temperature equal minus 60 degrees Fahrenheit to up to 120 degrees Fahrenheit. Since the number of temperature value was not specified, we'll choose to recalculate every 10 degrees Fahrenheit. Output saturation vapor pressure. Develop a hand example. The Clausius-Clapeyron equation requires that all the variables have consistent units. This means that temperature need to be in Kelvin. To change degree Fahrenheit to Kelvin, we use the conversion equation. This equation, temperature in Fahrenheit degree plus 459.6 divide 1.8, that's equal in Kelvin unit. There are a lot of places to find unit conversion. The internet is one search, as the science and engineering textbook. Now we need to solve the clausius clapeyron equation for the saturation vapor pressure. We have equation like this, and the next is for one temperature, for example T equal 0 degree Fahrenheit. Since the equation requires temperature in Kelvin, we must perform the unit conversion to obtain. If the 0 Kelvin is if the 0 Fahrenheit, we can 0 Fahrenheit equal to 155.3333 unlimited number Kelvin. Finally, we substitute value to get what is the VO equal 1.5836 millibar. Okay, we use MATLAB to as the solution to solve this equation. For example, this is the script of the MATLAB. If we input in the MATLAB program, what will happen? Let's try. Okay, first of all, we define the temperature metric in Fahrenheit. Okay, we write 10 F equal get this. What's wrong? Oh, sorry. That's clear. Okay, let's try. Sorry, I got nervous. And this the conversion from the degree Fahrenheit to degree Kelvin. Okay. And this is the workplace. We can find the name of variable and the value of variable, and this is the minimum of the value of variable, and this is maximum max value of variable. That's the in Kelvin. This in Fahrenheit. It is the value we get from the conversion from the Fahrenheit to Kelvin. Okay, we continue to this script. We define the delta H equal this to 2,000,045. It is the value of delta H, and the air constant 461. This is the air constant. And next we calculate vapor pressure. Okay, we calculate the vapor pressure. That is the vapor pressure. We find the value of the vapor pressure minimum 0.0698 and the maximum 118.19. Okay, it is the value we get after the substitute from the 0 degree Fahrenheit, and if we compare with this MATLAB result, is different, but around the between the value in the minimum and maximum we find the same like the manual solution. Okay, let's continue. We will make the result in the table. Okay, we use this command. Okay, this the value can table it. Okay, you will find if the the temperature 0 Fahrenheit, we will get vapor pressure 1.588 millibar. That is the equal with the manual solution. Okay, do you get clearly definition of the vapor pressure? Let's continue. Okay, that is the one of comment in MATLAB. We will definitely easy to follow it. Okay, I hope you can understand what I described from the first until the last. Thank you for your nice attention. Hope you got new insight in the equation application. Thank you.